So we got, as promised, we got one more collection of problems. This time I'm looking at section H, which deals with quotient groups, and in particular, the circle group. This is a question that's kind of close to my heart because in my line of work, I work primarily with complex numbers and also with algebraic geometry. And so, I can't resist the opportunity to talk about complex numbers. So, to get started, Pinter tells us that we have complex numbers, which we represent as expressions of the form a plus bi, where here is the normal real part, and here is the imaginary part, which gets this I. And so a plus bi is living somewhere like here, having coordinates a and b in the complex plane. And what can I say? This isn't a whole crash course in complex numbers. I'm going to assume that you know this. At least you know about these. What he tells us that we have to know is that complex numbers that live on the unit circle can all be written as cosine x plus I sine of x for some x in R. These live on unit circle. And we can see that if we're not completely convinced because, as real numbers, this would be the ordered pair cosine sine. And of course, we know the distance formula for the origin, right? That would be cosine squared plus sine squared, square root. But by Pythagoras, right, this is the Pythagorean identity that's 1. So they do, in fact, live on the unit circle. Okay, so what are the questions? The first part says that we write cis x for this expression, and we're asked to prove that cis of x plus y equals cis of x, cis of y. And indeed, we can do this. Cis of x plus y is cosine x plus y plus I sine of x plus y. Whereas cis x, cis y is cosine x plus I sine x, cosine y plus I sine y. And then we expand this guy on the right. I get cosine x, cosine y, plus I cosine x sine of y, plus I sine of x cosine y. And then we get I squared, which we have to just know is how complex numbers work, is minus 1, is sine x sine y. And so now let me collect the real and imaginary parts. The stuff without the i's is cosine x cosine y minus sine x sine y. And with the I is plus an I cosine x sine of y plus sine of x cosine y. And at this point in time, you go pause the video if your trigonometry is not up to date, and you go check that the real part of cosine of x plus y, right, this is the real part, this is the real part, that this in fact is equal to this. And the imaginary part, right here, you go check if you don't already know that that is equal to that. So it's correct. Okay. Now, Pinter says for part 2, we will call the unit circle T. And then he says, using what we just saw, show that T is a group under multiplication. Okay, so the identity element is 1, right? The unit complex numbers. And so of course, the identity is the complex number 1. 1 is equal to 1 plus 0i, or cosine of 0 plus I sine of 0, right? Sine of 0 is 0. cosine of 0 is 1. So this is a perfectly good element of this group. Part 1 handles the closure under multiplication. Right, we just checked that if I multiply two things of this form, I also get something of this form. Lastly, we need the inverses. And you could do this in two different ways. One of them is if you know a lot about complex numbers, it's pretty easy to convince you. You could just, if you know complex numbers, this is obvious. But if you don't know a lot about complex numbers, cosine of minus x plus I sine of minus x will do it, because when I take this guy and I multiply it by cosine x plus I sine of x, then we just saw that this is equal to what you get when you add them, which is cosine of x minus x plus I sine of x minus x, which is cosine of 0 plus I sine of 0, which is that unit number that we just figured out. And that deals with part 2. Okay, part 3. F of x equals cis x is a homomorphism from R to T. And yeah, I mean, what to say? This is also basically part 1. Part 1 shows us that f of x plus y equals cis of x plus y equals cis x times cis y. And here the operation is addition, which it is on R, and on T the operation is multiplication. So it's true basically by definition. We did it. What is the kernel of this? That's what question 4 asks us. Kernel of f. Well, we have cis of x equals cosine x plus I sine of x. And we know cis of 0 is 1. So 0, which is an element of R, maps to 1. Identity goes to identity. We know that that has to happen, right? F of E has to equal E. Well, cosine and sine are 2 pi periodic. And that's the minimum period. In other words, there's no smaller number that you can plug in, that you can translate x by and have it agree for all values of x. And so what that means is you'll get back to 1 every copy of 2 pi. And we know that. That's like the unit circle again, right? Here's our nice unit circle. Every time I go 2 pi around, I get back to 1. So therefore, kernel of f is exactly the multiples of 2 pi. All right. Pinter uses the notation for this 2 pi as a subgroup of R. That's fine too. Okay, so therefore, by the fundamental homomorphism theorem, there is a typo in Pinter, but that's fine. By the fundamental homomorphism theorem, I have R to T via this map H. The kernel is 2 pi. So we get an isomorphism from R mod 2 pi to T. And we see that T is isomorphic to R mod 2 pi. Okay. And part 6 and 7 are basically a rephrasing of this, where we just modify the homomorphism. They say instead, how about you use g of x, which is cis of 2 pi x? Yeah, 2 pi x. And what can I say? The proof is exactly the same. I'll let you guys pause the video if you want to and verify that the above math all works the same. But in this situation, the kernel is now exactly just the integers because of the scaling. And so therefore, T is also isomorphic to R mod Z. And in fact, this is often called the circle group instead of the 2 pi. And so this can be slightly a little bit misleading, but really what this is showing is, as you can mod out R by any discrete. Is that true? Hold on. I think it's true. Slightly unsure. Because I'm pretty sure that any discrete subgroup of R has a minimal non-zero generator, and in particular is therefore cyclic, and therefore isomorphic to Z. But what this is showing is this expression is also, right, this 2 pi is also isomorphic to Z. So in particular, what we're seeing is T can be realized as R mod Z for different isomorphism classes of Z. So in other words, there are different isomorphic versions of Z in R. Any non-zero real number defines a copy of Z in R by looking at its multiples. And so we can write T equals R mod different stuff, and those are all R mod Z's, and they're all isomorphic groups. The resulting quotients are isomorphic, but not equal. And I think this is an important point that I don't think we've emphasized much up until now, which is that they can't possibly be equal, right? Because their cosets are different. These ones differ by multiples of 2 pi. These ones differ by multiples of 1, right? These are different elements here. The homomorphism, realizing this quotient, builds that factor in, but the equivalence class of the quotient doesn't know that. It just knows, here I'm taking so-called the decimal part, right? Chopping off the stuff before the decimal point. This is looking at things mod 2 pi, right? You can think of this as like looking at your angle on a circle. And those are different, but related by the fact that they're a 2 pi angle in a full turn of the circle. Hopefully that makes sense. If not, I think it's worth it to take this time and kind of meditate on that for a little bit. Turn that over in your mind until you can see the distinction between equal and isomorphic. And I think that's it, friends. I think we're going to call it here. There are a whole bunch of cool problems in this section, some of which I've picked out for you guys. And after that, when you're satisfied, we are going to be done with week 6 and therefore ready to start building in the direction of a whole new branch of abstract algebra, namely fields. And of course, it's not an unrelated branch. We're going to be spending the remainder of our time in this class tying together the concept of group and field through the study of Galois theory. And I think that will make for a very nice capstone to our 8-week class. Looking forward to seeing you all there.